I'm a molecular systematist. Basically what I do is I collect insects, grind them up, sequence their DNA, and infer how they're related in phylogenetic relationships. So I've always been interested in insects, and my research is really focused on three main areas. I've been interested in the deep level phylogeny of insects all the way back to 500 million years, how the orders are related to one another. And then towards the tips of the tree, I've specialized on Trichoptera, or caddisflies. These are closely related to moths. The larvae have fascinating underwater case-making and retreat-making behaviors. And they are reliable indicators of water quality. So you can use biodiversity estimates of Trichoptera species to estimate pollution tolerances and pollution levels in streams. And then the third level of research that's always interested me is the technical aspects of creating trees and working on how trees are constructed, doing them well, modeling, homology assessment, alignment analysis. So those are really the three central foci of my work. But it's always centered around just a fascination for insects. Like a kid, I've always loved insects, and I feel honored to be able to work with them. We actually published about 1% of the data. We have something like 15 trillion nucleotides. This is the largest data set ever put together for phylogenetics. We have 1,400 taxa, each of them with maybe 15,000 genes. So the genes in common are maybe 3,000 to 5,000 in each of the groups. But with a data set that size, we split into a strategy of publishing the first paper with just 100, actually 144 taxa. And what we're working on right now is specialists are working on their own group. So there's a Hymenoptera group, there's a Trichoptera group, a Lepidoptera group. There's about 10 taxonomic specialists working on their own group. And the nice thing about this is that they can lead a large project, and it's hard with 100 authors to motivate the 78th author to really dedicate the time they need. So we're putting specialists in charge of the taxonomic subgroups. And these are being worked on right now, and in the next 2 years, we should be publishing papers on all of the insect orders so that we get these 1,400 transcriptomes done, and we have an amazing taxon sample. Well, it's interesting. You can tell the age of insects simply by how cosmopolitan even families are. With many groups like mammals, for example, marsupials, they're in Australia, right? And that has to do with continental drift. But the continents were all together when most insects first evolved. So most insect groups are all over the world. And this is exciting for me because when I go to Australia and turn over a rock and the beetle looks just like the beetles that I would find in California, that tells me something about how old those groups are. And they have been in existence since the continents were one supercontinent. And it's like going in a time machine. If you went back to the Jurassic, as an entomologist, you would recognize insects to family. So if you think about the mammals that existed, eutherians didn't even exist at that time. So it's pretty amazing. There's huge advantages in the amount of data we can collect. It took me 20 years to sequence 2 million nucleotides total for about 200 taxa. And we can do that in 1 day now. So the amount of data we can apply to an evolutionary question is many orders of magnitude greater now. But there are new challenges with phylogenomics as well. So we have almost unlimited data, but we don't have an increase in the number of people. It still has to be analyzed properly, and we have to think about it. So it's probably more difficult to analyze than in previous days.